So, students, in last class we have seen electrostatic force, we have seen electrostatic potential energy, and we have seen what is electric field. We have just done basic introduction of electric field. So, let us quickly summarize what we have learned till now. So, in the first class we have learned that if there are two charges separated by a distance of r, they are going to experience a force which is called as electrostatic force, and the formula for electrostatic force was K Q1 Q2 divided by r square. This is the force in magnitude form. Next, you can write the same force in the unit vector form or in the vector form as K Q1 Q2 divided by magnitude of r square into r cap. Same thing can be written as K Q1 Q2 divided by magnitude of r cube into r vector, and finally you can write this thing as K Q1 Q2 divided by r2 minus r1 cube into r2 minus r1 vector. So, this is electrostatic force. Then we have seen electrostatic potential energy of two charges. Suppose there are two charges Q1 Q2, they are separated by a distance of r. The electrostatic potential energy of them can be given as K Q1 Q2 divided by r. Then finally we have seen electric field. Electric field we defined as force per unit charge, and we have found out the electric field intensity due to a point charge. So, due to a point charge, suppose you have a point charge q at a distance r at point P, the electric field intensity can be written as kq divided by r square. If the charge is positive, the electric field intensity will be away from the charge, and if the charge is negative, the electric field intensity will be towards the charge. So, electric field will be towards the charge for a negative charge, and electric field intensity for a positive charge will be away from the charge. So, this is we have done basically. So, one is force, this formula, second is potential energy, this formula, and third one is the electric field intensity due to a point charge. So, as you can see, all these formulas look very similar, but they are very different formula. Here you have K Q1 Q2 divided by r square, here you have K Q1 Q2 by r, and here you have K Q divided by r square. So, these two quantities, as you know that to experience force you need two particles, minimum two particles. Same way for potential energy also you need minimum two particles, but electric field is a quantity which is defined for one single particle. If there are multiple particles, then the total electric field intensity is given by the vector addition of all the electric field intensity. Till now this we have what we have done in last class. Now, let us do the problems which we have done in the last class. First problem which I gave you was, you have a square, on all the corners of the square you have q charges, inside of the square is A, at the center you have to find the electric field. This is a positive charge, this is also positive, this is also positive, this is also positive. So, due to this positive charge, here direction of electric field will be in this direction. Due to this positive charge, electric field intensity will be in this direction. Similarly, due to this charge, electric field intensity will be in this direction, and due to this charge, electric field intensity will be in this direction. As you know that these all the directions, all these lengths are equal. So, here electric field intensity magnitude will be equal. So, these two have same magnitude but opposite direction, so these will cancel. These two also have same magnitude opposite direction, so these two also again will cancel out. So, at the center net electric field intensity will be 0. Second problem was, here now you have minus q charge, here also you have minus q charge. Again, due to this minus charge, electric field intensity will be towards the charge. Due to this charge, electric field intensity will be away from the charge. Due to this charge, electric field intensity will be towards the charge, and due to this charge, electric field intensity will be away from the charge. So, again as you can see, magnitude wise all the electric fields are equal. These two are in the opposite direction, so they will cancel each other out. These two are also in the opposite direction, so these two also will cancel each other. Again, you will get the electric field intensity at the center as 0. And third problem was you have minus q charge. Sorry, here you have q charge, here you have minus q charge. Again, the electric field intensity will be only in these directions also. So, due to this q charge, electric field intensity will be in this direction. Due to this q charge, electric field intensity will be in this direction. Due to this minus q charge, electric field intensity will be along this direction. And due to this minus charge, electric field intensity will be in this direction. So, magnitude wise all the electric field intensities are same, but their directions are different. So, you have to do the vector addition to find the net electric field intensity. So, now let us find out the electric field intensity due to this charge. Again, this distance is a by root 2, a by root 2. So, electric field intensity due to this charge at this point, I can write E1 is equals to k q divided by r square, which will be a square by 2. So, this will be 2 k q square by a square. So, electric field intensity due to this will be 2 k q by a square. Similarly, due to this charge, electric field intensity will be 2 k q by a square. Same for this charge, electric field intensity will be 2 k q by a square. So, magnitude wise all the electric field intensity are same. Now, let us find out what is the net electric field intensity. So, this one and this one vector are parallel. So, their vector addition will be 2 k q by a square plus 2 k q by a square. So, I will have a vector which is in this direction and it will be 4 k q by a square. Similarly, these two are also parallel. So, the resultant of these two also will be 4 k q by a square. Angle between them is 90 degree. So, what will be the resultant of these two charges? Resultant of these two vectors will be along this direction, which will be root 2 into 4 k q by a square. This is your net electric field intensity. Direction of net electric field intensity will be along this direction. So, as you can see, we have done the similar problem in the finding the force also. So, same problems can be done for electric field intensity also. So, vector quantities, we have seen, we have done these kind of problems in gravitational field also. The next problem was you have two charges. This is 2 coulomb charge, this is 8 coulomb, and distance between them is 8 meter, and you have to find the electric field intensity at the midpoint. Now, as this charge is positive, so due to this electric field intensity will be along this direction, and this is also positive. So, due to this charge, direction of electric field will be away from the charge. So, the electric field intensity will be in this direction. This electric field intensity I can write k into q divided by this distance will be 4. So, this will be 16, and electric field intensity due to this one will be k, this was 4. Due to this it will be k 4 divided by 16. So, as you can see, now you have two vectors, both the vectors are in the opposite direction. So, how do you find the resultant of these two vectors? The resultant will be the bigger vector minus smaller vector. So, this will be 4k by 16 minus 2k by 16. So, net electric field intensity will be 4k by 16 minus 2k by 16. So, this will be equals to 2k by 16. This is the answer. Here you can put the value of k as 9 into 10 to power 9 into 9 into 10 to power 9. Direction of this electric field, as this electric field is more in the magnitude and this is less in the magnitude. So, net direction of electric field intensity will be along this direction. So, in last class we have defined the electric field. Electric field is the space around the charge in which another charge experiences a force. So, you have a charge q around this charge in this space. there is electric field. In this electric field, if you bring a charge q, this charge is going to experience the force, and we have defined that force per unit charge as electric field intensity. Now, if I want to find the force on this charge, what should I do? Force on the charge can be written as E is equals to F vector divided by Q. From here I can write electrostatic force can also be written as Q into E. Now, here this formula is very simple, but you have to remember what all these quantities mean. This F is the force experienced by the small q charge. So, remember this, when you are writing the electrostatic force, you are finding the force on this charge, and here this q is magnitude of this charge, q is So, in last class we have seen electric field, and we have defined electric field intensity and what is electric field. We have defined electric field as the space around the charge in which another charge experiences a electric force. Suppose you have a charge q, it is going to produce electric field in a space around it. If you bring another charge q in this electric field, this charge is going to experience the force. Now, I want to find the force on this charge. Suppose now you know the electric field, you want to find the force on this charge. We have defined electric field as force per unit charge. So, from here I can write electric force will be equals to Q into E. Now, remember this F is the force experienced by this charge, and this is the E, which is electric field produced by this charge. So, when you are writing the force on a charge, remember you do not write the force, you do not write the electric field produced by the charge on you do not write the electric field produced by the charge itself, you write the electric field due to other charges. So, electric force is charge into the electric field produced by the other charges. So, this is the very simple formula for electric force when you know the what is electric field. Same way as we have defined gravitational field, we said that gravitational field is the space around the mass in which another mass experiences the gravitational force. If I ask you, can you see the gravitational force, can you see the gravitational field, your answer will be no. Similarly, electric field also cannot be seen. So, electric field is invisible, you can only experience it, just like you can only experience the gravitational force, you can only experience the electric electric field, you can experience the electric field, but you cannot see this. So, to represent the electric field on paper, we make use of some lines, and we call those lines as electric field lines. So, next topic will be electric field lines and their properties. So, heading is electric field lines and their properties. Now, as I said, electric field cannot be seen. So, to represent on the electric field on the paper, we make use of some lines. Those lines are called as electric field lines. As you know, as you realize that electric field cannot be seen, so whatever lines we are drawing, those lines are basically imaginary lines. Now, to visualize this thing, suppose you have a bulb. You might have done this thing in your lower classes, class 10th. There is a bulb. If you want to show that this bulb is glowing, what do? You normally draw the lines like this. If you are drawing the lines like this, it means that this bulb is glowing, and if you are not drawing these lines, it means that the bulb is in the switch off state. Same concept, from the same concept we have derived the concept of electric field lines. So, suppose you have a positive charge, it is going to produce electric field around this. So, but we cannot see that electric field. So, to represent that electric field, we are going to use electric field lines. Suppose if I ask you what is the direction of electric field intensity here, sorry, electric field here, you can say this charge is positive. So, due to this positive charge, direction of electric field will be along this direction. Similarly, if the charge was here, sorry, at this point electric field intensity will be in this direction. If the point is here, the direction of electric field intensity will be in this direction. Similarly, if the point is here, direction of electric field intensity will be in this direction. So, if I want to write the electric field intensity at every point, I can simply represent this as like this. So, as you can see, for a positive charge, electric field lines will be always away from the charge going outwards. Similarly, for a negative charge, electric field will be towards the charge. So, we can draw the electric field lines like this for a negative charge. So, for a positive charge, electric field lines are away from the charge, and for a negative charge, electric field lines are towards the charge. So, now that we have defined what is electric field lines, now let us see what are the basic properties of electric field lines. You can write down first property of electric field lines. So, as we have seen that electric field lines are going away from the positive charge, and for a negative charge electric field lines are coming towards the positive charge. So, first property of electric field lines are electric field lines originate on a positive charge. As you can see, this is a positive charge. So, they are originating from the positive charge, and they terminate on a negative charge. So, we have written first property of electric field lines is electric field lines originate on positive charge and they terminate on negative charge. So, this is the first property of electric field lines. Now, second property of electric field lines, we have defined electric field as force per unit charge. So, I can write electrostatic force will be equals to Q into E. Now, if the force, this charge is a positive, the direction of the force and direction of electric field will be same. If the force is, so this charge is negative, then the direction of the force and the direction of electric field will be opposite. So, I can say direction of electric force will always be along the direction of electric field lines. Suppose you have electric field lines like this, suppose you have an electric field line like this, if the charge is positive, the force on the charge will be in this direction. If this charge is negative, the force on this charge will be in the opposite direction. So, I can say the force will be along the electric field lines. Now, we are going to write the second property of electric field lines. So, second property of electric field lines is electric field lines also gives the direction of electric force. Electric field lines also gives the direction of electric force. That is why they are also called as electric line of forces, electric lines of force. Electric field lines also gives the direction of electric force. So, they are also called as electric lines of force. Now, we are going to see the third property of electric field lines. Now, third property of electric field lines are electric field lines never intersect each other. Electric field lines never intersect each other. Now you might ask, why electric field lines never intersect each other? Suppose I have two electric field lines. One electric field is along this direction, one electric field line is along this direction. Suppose they are intersecting each other at this point. Now as we know that electric field lines gives you the direction of electric field at a point. So if I ask you what is the direction of electric field here, there will be two possible directions. One will be along this electric field line, second will be possible along this direction. So now you have a vector which has two directions, which is not possible. So from this you can say that two electric field lines never intersect each other, because if they are intersecting at a point, there will be two direction of electric field, which is not possible. So you can write this explanation why two electric field lines never intersect each other. Two electric field lines never intersect each other because at the point of intersection, electric field will have two directions. Electric field will have two directions, which is not possible. So first property of electric field lines was electric field lines originate from the positive charge and they terminate on the negative charge. Second property was electric field lines also gives you the direction of the force, so you call them as electric lines of forces. Third property of electric field lines is two electric field lines never intersect each other, because if they are intersecting each other at the point of intersection, they will have two directions, which is not possible. Next property, fourth property. Fourth property is electric field lines do not make closed loop. Electric field lines do not make closed loop. What do you mean by this thing? Electric field lines can never be like this or like this or any other loop which is possible. So they cannot be in any loop. So you cannot write this is electric field lines. Electric field lines will never look like this. Now explanation for this is, it comes from the fact that electric field is a conservative field. Now as we know, in a conservative force, the work done in a closed loop should be 0. So if you are starting from this point and you are again going through this path and coming at this point, the total work done should be 0. So if you start from here, the force will be in this direction, here the force will be along this direction, here force will be along this direction, and here force will be along this direction. And when you reach here, if you calculate the total work done will not come out to be 0. So if electric field lines were to make closed loop, the total work done in closed loop will not be 0. So if the total work done is not 0, then electric field cannot be conservative. So from this fact you can say that electric field lines never make closed loop, because if they are making a closed loop, electric field will not be a conservative force. So you can write the explanation why electric field lines do not make a closed loop. Electric field lines do not make a closed loop. Electric field lines do not make a closed loop because electric force is a conservative force. And for a conservative force, the work done in a closed loop should be 0. For a conservative force, the work done in a closed loop should be 0. So this is the fourth property of electric field lines, which is electric field lines do not make a closed loop. So we have seen electric field lines and their properties. In those properties, till now we have written 4 properties. Out of those 4 properties, 3 properties are important. First one, which is electric field lines originate from the positive charge and they terminate on the negative charge. Second property, which we have said, that electric field lines are also called as electric lines of forces. That is for your knowledge purpose, that is not going to ask you in the exam, or they might mention electric field lines as electric lines of forces. So electric lines of force. Third property we have written as electric field lines do not intersect each other, and fourth property is electric field lines do not exist in a closed loop. Now next property of electric field lines is suppose you have positive charge. For this positive charge, electric field lines will look like something like this. If I ask you what is the electric field intensity due to a positive charge, electric field intensity can be written as E is equals to kq by r square. Now from here you can see as the r is increasing, electric field is decreasing. So where r is the distance of the point from this charge. So here suppose electric field is EA, point A, and here electric field intensity is EB. You have point B, you have point A. So if the point A electric field intensity is EA and at the point B electric field intensity is EB, you can say electric field intensity at point A is more than electric field intensity at point B. Now if you look on this diagram, you can see that here electric field intensity is more and the lines are very close to each other. At this point electric field is less and electric field lines are further away from each other. So next property of electric field lines you can write as intensity of electric field lines, intensity of electric field is directly proportional to density of electric field lines. Or in simpler word, if the electric field lines are closer, electric field intensity will be more. If the electric field lines are further away from each other, electric field intensity will be less. So this is the fifth property of electric field lines. Next property of electric field lines is number of electric field lines originating or terminating, number of electric field lines originating and terminating are directly proportional to the magnitude of the charge. Number of electric field lines originating or terminating are directly proportional to magnitude of the charge. Now what do you mean by this thing? Suppose they give you two charges or they give you 2 points and they ask you which charge has more magnitude. As you can see from this charge there are more number of lines originating, so this charge will have more magnitude. This charge has only 1, 2, 3 and 4 lines, this charge has 8 lines. So magnitude of this charge is double of this charge. So last property of electric field lines is the number of electric field lines originating or terminating from a charge is directly proportional to the magnitude of the charge. If magnitude of the charge is more, electric field lines will also be more. From here, if I ask you which of the following charge is positive, as you can see from this charge the electric field lines are originating, so this charge will be positive charge, and this charge the electric field lines are terminating on this one, so this will be minus charge. So again I repeat, electric field lines, their properties, first property is electric field lines originate from the positive charge and they terminate on the negative charge. Second property is they are also called as electric lines of force. Third property is two electric field lines do not intersect each other because at the point of intersection there will be two direction, which is not possible. Fourth property is electric field lines do not exist in the closed loop because if they are existing in a closed loop, electric force will not be a conservative force. Fifth property is if the lines are close to each other, the electric field intensity will be more. If the lines are away from each other, electric field intensity will be less. Next property, final property is the number of lines originating from a charge and terminating on a charge is directly proportional to the magnitude of the charge. If the magnitude of the charge is more, number of lines will be more. If the magnitude of the charge is less, number of lines will also be less. So these are the important properties of electric field lines which you should know. There are more properties of electric field lines, but we will see those in later sections. Now we are going to do a question based on the properties of electric field lines. Question is, which of three charges of same nature and magnitude, are placed on corner of equilateral triangle. 3 charges of equal magnitude and nature are placed on corner of equilateral triangle. Which of the following correctly represents the diagram of electric field lines? Which of the following correctly represent the diagram of electric field lines? So your first option is, you have 3 charges So you have 3 charges which are placed on the corner of a equilateral triangle, and you have to find which of the following diagram correctly represent the diagram for electric field lines. Pause the video and try to think about this thing. So as the question is saying, the nature of the charge is same and the magnitude of the charge is also same. So from that you can say that either the lines will originate from the charge or they will terminate on the charge. In the first diagram, as you can see, the lines are originating at this point and they are terminating on this point, or they are originating at this point and they are terminating on this point. So this is not the correct representation of electric field lines. This is straightforward incorrect, because here the electric field lines are making closed loop, so this is also incorrect. Similarly, here also electric field lines are making closed loop, so this is also incorrect. So this will be the correct answer. As you can see, if these charges have same nature and same magnitude, number of lines are 3 and 3. So magnitude is the same. If you draw the arrows like this, so they represent that all the charges are positive, and if you represent the arrows like this, it will mean that the charges are negative. So next thing we are going to define is electric potential. So you can write the definition of electric potential. Electric potential is work done. Electric potential is work done to move 1 coulomb charge. Work done to move 1 coulomb charge from reference point to a specific point, from reference point to a specific point in electric field is called as electric potential. Work done to move 1 coulomb charge from reference point to specific point in electric field is called as electric potential. Now, if you read this definition again and again, it will make no sense to you. So, I am going to give you a very simple definition of electric potential. Electric potential is simply electric potential energy per unit charge. So, definition of electric potential for your understanding purpose, you can say electric potential is potential energy per unit charge. So, whatever energy is required to move a charge from one point to another point, divide that energy by the charge, you will get the electric potential. Now, as you know that electric field potential energy is a scalar quantity, charge is also a scalar quantity. So, electric potential is also a scalar quantity. So, electric potential is a scalar quantity. Second, let us talk about the unit of electric potential. Unit of electric potential can be written as joule per coulomb. And the name given to this unit is volt. So, SI unit of electric potential is joule per coulomb, which is also called as volt. Potential is defined as potential energy per unit charge. This is the simplest definition, the definition given in the book which I have dictated. Similarly, from this I can write a change in potential will be change in potential energy per unit charge. So, the potential is potential energy per unit charge, change in potential is change in potential energy per unit charge. Unit of both of them is joule per coulomb, which is also called as volt, and they are a scalar quantity. Next is we are going to do the relationship between electric field and potential. Relation between electric field intensity and potential. So, if you remember the relationship between potential energy and the potential energy and the force is delta U is equals to minus of integration F dot dr, or for in this case I can write electrostatic force. So, this is the change in electrostatic potential energy, which is from R initial to R final, Fe dot dr. If I divide this quantity by Q, here I will get delta U by Q. This will be also delta Fe by Q. This quantity, change in potential energy per unit charge, can be written as change in potential. Here I can write force divided by charge can be written as electric field. So, I can write this thing as electric field intensity dot Tr. So, this is from R initial to R final. So, if you look closely, both the relationship between potential energy and the force and the relationship between potential and electric field are very similar. So, change in potential can be written as minus of integration E dot dr from R initial to R final, the same thing we have done for change in potential energy. So, this is the relationship between electric field and potential. In previous class, we have done the relationship between the potential energy and the force also, where we have found out the if the potential energy is given, how do you find the force? Similarly, if the potential is given, how do you find the electric field? So, now we are going to find the electric field if the potential is given. As you know that electric field intensity is a vector quantity, so you can find all the component of the vector, then you can find the total vector. So, x component of electric field can be written as minus of dou v by dou x So, in last class we have seen the relationship between the potential energy and the force. So, if the force is given, you can find the change in potential energy, and if the potential energy is given, you can find the force. Similarly, just now we have seen if the electric field is given, you can find the change in potential. Similarly, if potential is given, you can find the electric field by this relation. We have in the last class we have written electrostatic force can be given by dou u by dou x I cap plus dou u by dou y j cap plus dou u by dou z k cap. If I divide this whole equation by q, I will get F by q, which will be electric field. Here this u by q will become v. So, I can write this thing as minus of dou v by dou x I cap plus dou v by dou y j cap plus dou v by dou z k cap. So, this will give you the x component of the electric field, this will give you the y component of the electric field, and this will give you the z component of electric field. Now, last thing which we are going to do is electric field in vector form. In first class we have seen electrostatic force in the vector form, from that we can derive how to write electric field in vector form. So, electric field in vector form can be written as F by Q. F can be written as, in vector form F can be written as K Q1 Q divided by R magnitude of R square into R cap. So, from here I can write electric field in vector form will be K Q by R square into R cap, which can be written as R cube R vector or R2 minus R1 magnitude into R2 minus R1. As you can see, the formulas are very similar. You have to remember this R cap is the position vector, sorry, R cap is the unit vector, R vector is the position vector, and this is the displacement vector. Here R2 will be the point at which you want to find the electric field, and R1 is the point at which the charge is placed. So, you can write this. So, let us quickly summarize what we have learned till today, till now. We have learned about the relationship between electric field and the force, which can be written as F by Q. Then we have seen the relationship between the electric potential and the electric potential energy. V can be written as U by Q, or it can be written as delta V is equals to delta U by Q. Then we have seen the relationship between electric potential and electric field, which is delta V is equals to minus of integration R initial to R final E dot dr. So, this is what we have learned today. From this we are going to do some problem which have come in the previous year exams, in previous years which have come in the exam, and we are going to proceed further with electric field and potential. Now, our main focus will be on the electric field and potential. We are done with the mechanics part, where we talk about electric force, we have talked about electric force and potential energy. Now, we are only going to talk about electric field and electric potential. From this point onwards, the chapter is going to become slightly complicated, not too complicated, but if you revise it daily, it will be very easy. Okay, we are going, so for you today there is no homework, you can revise whatever we have learned till now, and my advice will be to revise your vector addition, because we are going to use vector addition again and again. So revise vector addition and revise whatever we have done till now. So I will see you in the next class. Thank you.